Ever get that feeling that your music gear is speaking a language you only partially understand? Like there's this secret handshake that unlocks even more creative potential from your synths and drum machines.
That's spot on. Yeah. It's like discovering the fundamental building blocks, of how these electronic instruments actually talk to each other.
Exactly. Well, you've tuned into the right place. Today on the deep dive, we're cracking the code of CV Gate. We'll explore what it is, where this method came from, and most importantly for you, the listener, how it's still a powerful force in modern music production.
Definitely. And this isn't just a dusty history lesson. CV Gate is really a vibrant part of today's music creation, offering some pretty unique possibilities.
Couldn't agree more. So to really get a solid understanding, we've dug into resources like the Synthesizer Wiki's detailed explanation, some really insightful articles from places like Such Music and Perfect Circuit, and the overview on Wikipedia too.
Right.
Our goal, like always, is to basically distill the essential knowledge and the practical stuff directly for you.
Yeah, we want to go beyond just saying, oh, it existed, and actually show you how it can be a hands-on tool, like in your current creative process
Hmm.
right now.
Okay, so let's get practical then. What is CV Gate in simple terms? It sounds maybe a bit abstract, but the core
Yeah.
idea is quite accessible, isn't it?
Oh, absolutely. At its heart, CV Gate is an analog way for different pieces of electronic music gear, mainly synthesizers, drum machines, that sort of thing, to interact
Uh-huh.
and be controlled by external devices like sequencers. Think of it like sending instructions through, well, varying electrical voltages.
Okay, instructions via electricity. And the two key elements in this instruction set are CV and gate. Let's start with CV. What kind of information does that carry?
Right, CV stands for control voltage. Primarily, it governs the parameters of a sound. The most
Okay.
common one everyone thinks of is pitch. Different voltage levels dictate different musical notes.
Good.
The key thing here is that voltage directly translates to musical expression. It offers this really immediate and, I think, intuitive way to manipulate sound.
So but basically, more voltage equals a higher note, and less voltage means a lower note. Something like that.
Generally, yeah, that's the idea. However, here's where it gets a little nuanced in practice, maybe slightly tricky. There aren't universal voltage standards for pitch. You'll mainly run into two systems, volts per octave and hertz per volt.
Okay, let's unpack those a bit. Volts per octave sounds pretty straightforward.
It is, relatively speaking. This system, famously championed by Moog and then adopted pretty widely by Roland, ARP, Sequential Circuits, Oberheim,
Yeah.
and it's the standard for Euro rack modular synths, from Doepfer.
Ah,
It assigns 1 volt to represent exactly 1 octave. So if a certain voltage gives you a C note, a voltage exactly 1 volt higher will give you the next C up.
right.
It's a linear relationship, and each 1 volt octave has 12 equal semitones within it. Nice and logical.
Makes sense. What about hertz per volt then? That sounds more
Okay.
technical.
It is a bit more technical, yeah. This system, favored by most Korg and Yamaha synthesizers, takes a different approach. Instead of that linear progression, doubling the voltage corresponds to 1 octave.
Doubling. Okay.
So if 1 volt gives you a certain frequency, say 100 hertz, then 2 volts will give you 200 hertz an octave up. 4 volts would be 400 hertz, another octave. It's an exponential relationship.
Ah,
Understanding these different tuning standards is, well, pretty crucial for seamlessly integrating vintage gear and even some modern analog stuff. It prevents frustrating out-of-tune results.
okay. So if I tried to connect, say, an old Korg using hertz per volt directly to a Moog, using volts per octave to control pitch,
Yeah.
I'd probably run into some tuning headaches.
Oh, precisely, yeah. They aren't directly compatible for controlling pitch accurately. But the good news is that devices exist, like the old Korg MSO2 interface, for example, that can convert between these standards. So there are practical solutions for integrating different gear.
Good to know there are translation tools available. Phew. Now, you mentioned CV can control other aspects of sound besides just pitch. What else can voltage manipulate?
Oh, just about any parameter that shapes the sound over time or defines its character, really. Common examples are things like filter cutoff frequency,
Right.
LFO speed, LFO intensity, amplifier volume, essentially any knob or setting you might want to automate or dynamically change.
Hmm.
In these cases, the CV usually operates within a specific voltage range, like 0 volts to 5 volts was common on older Moog systems, where 0V might be the minimum setting and 5V the maximum.
Okay, that clarifies what control voltage does pretty well.
Right.
Now let's talk about the gate part of CV gate. What's its role in this whole analog communication thing?
Right, the gate signal. It
Yeah.
acts basically as an on-off switch for a note or a sound event. It tells a device when a note should start playing and how long it should last.
Okay, on, off, and duration.
Yeah. When a key on a controller is pressed, the gate signal typically goes high, it reaches a certain voltage level, and it stays high for as long as you hold the key down.
Uh-huh.
Releasing the key causes the gate signal to go low again, usually back to 0 volts, signaling the note to stop, so it's directly tied to the timing of a musical event.
So it's the when and the for how long instruction.
Exactly. Now, related to the gate, but slightly different, is the trigger signal. They're often used together, but they serve slightly different purposes.
Okay. How does a trigger differ in its function then?
A trigger is more like a very brief pulse, like a quick tap. It marks the precise instant a note or event should start.
Just the start.
Just the start. It's often used to initiate an action, maybe like starting an envelope generator. You know, the thing that shapes the attack, decay, sustain, release of a sound.
Ah, okay. So the envelope needs that go signal.
Precisely.
And a gate signal sustains for the whole length of the note, whereas a trigger is just that momentary blip at the beginning.
Correct. You've got it. The trigger is that initial impulse, the start now command, while the gate provides the duration for which the sound should be active or maybe a modulation should be applied.
I think the synthesizer wiki mentioned different kinds of triggers too, like voltage trigger and short circuit trigger. What's the practical difference there? Is that important?
It can be important for compatibility, yeah.
Yeah.
There are a couple of main ways these start signals are implemented. The most common, voltage trigger, or v-trig, uses the presence or absence of a voltage signal.
Okay.
Typically switching between 0 volts and around 5 volts, though some older Roland and ARP gear could go even higher, like up to 15 V. When the voltage goes high, it triggers the event. Simple enough.
Right.
Short circuit trigger, or s-trig, which you'll find mainly on older Moog and some vintage Korg synths, works differently. It involves briefly connecting a circuit contact to ground to 0V to initiate the trigger.
Shorting it out, basically.
Kind of, yeah. Knowing this difference is important for compatibility, definitely.
So you really need to be aware of what type of trigger your specific device expects when you're hooking up different brands of gear. Absolutely. Connecting an incompatible trigger system might just result in, well, no sound, or maybe even the opposite of what you intended. But again, fortunately, converters exist to translate between v-trig and s-trig, so it's a solvable problem, offering a practical fix for integrating diverse vintage gear.
Okay, great. So we've got a pretty solid understanding now of what CV and gate actually are. Let's maybe take a step back and look at why this system emerged in the first place. Why did early electronic musicians rely on these voltage signals? What was the problem they were solving?
Yeah, it's fascinating context. To understand that, you kind of have to picture the really early days of electronic music studios. We're talking post-war era. Instead of dedicated musical instruments like we have now, they were often filled with scientific test equipment. Oscillators, filters, noise generators.
Stuff from labs, basically.
Exactly, stuff repurposed to create sounds, even though that wasn't their original design at all.
So making music involved a lot of, like, manual patching with wires and then painstakingly editing physical tape.
Yeah.
Sounds tedious.
Oh, incredibly tedious. Composers would connect these devices, record the results onto big reel-to-reel tape machines, and then the really laborious process of cutting the tape with razor blades, splicing bits together, reversing sections, changing playback speeds, that would begin.
Wow.
There was naturally this strong desire for a more immediate and interactive way to create music, something closer to actually playing a traditional instrument.
And the idea of voltage control provided that solution. That was the breakthrough.
Exactly. Pioneers like Harold Bode and Hugh Kane, and then a bit later, Bob Moog and Don Buchla, they independently came up with this idea that these specialized musical devices could influence each other's behavior using voltage signals. This led directly to the development of the modular synthesizer, these collections of purpose-built, voltage-controlled modules like oscillators, filters, amplifiers, envelope generators, all housed together in a single unit with a standardized way to connect them using patch cables.
So instead of just routing the audio signal around, you could now use a control voltage from, say, a sequencer module to directly manipulate the pitch of an oscillator module in real time.
That's the absolute core innovation, yeah. CV allowed for automation and dynamic changes that previously required laborious manual tweaking or those tedious tape edits. You could use an LFO module to automatically sweep a filter or a sequencer module to play a melody without manually adjusting knobs for every single note.
Game changer.
Totally. CV gate became the fundamental language for these early electronic music instruments to communicate and synchronize with each other.
And this CV gate standard continued even as synthesizers evolved into more self-contained units with keyboards built in, like the Minimoog.
Yes, absolutely. Even those early self-contained monosynths like the Minimoog or the ARP Odyssey, they often included CV and gate inputs and outputs.
Ah,
This allowed musicians to, for example, use the keyboard of one synthesizer to control the pitch and triggering of another synth module, or even a whole other synth, offering really expanded sonic possibilities. It was the primary way electronic instruments communicated before MIDI arrived.
which brings us neatly to the rise of MIDI. I know that eventually became the more prevalent standard for a long time. What impact did MIDI's introduction, what was it, 1983, what impact did that have on CV Gate?
Right, 1983. MIDI was a huge leap forward in many ways. It could transmit much richer performance data, things like how hard you hit a key, velocity, patch changes, aftertouch, and crucially, support for playing multiple notes at once. Polyphony.
Ah, yeah, polyphony was a big deal.
Huge deal. And it used standardized cables, simplified connections. It just became the go-to protocol for interconnecting digital musical instruments pretty quickly. So for many applications, MIDI did effectively take the place of CV Gate for a while.
So did CV Gate just sort of become obsolete then? Did it die out?
Not at all, actually. It might have seemed that way in the mainstream for a bit, but the modular synthesizer world, which had always relied on CV Gate, just kept chugging along.
Oh.
And then in recent decades, we've seen this really significant resurgence in the popularity of analog gear, both fully modular and semi-modular synths.
Right, the Eurorack explosion.
Exactly. And many modern synthesizers now, even desktop units or effects pedals, they now feature CV Gate connectivity right alongside MIDI ports, offering kind of the best of both worlds. So CV Gate never truly went away, and now it's experiencing a really strong revival.
So it's not really an either choice anymore. It sounds like we often see both MIDI and CV Gate capabilities coexisting in today's music technology.
Exactly. A hybrid approach is actually very common now. Musicians frequently use MIDI for general sequencing duties, maybe controlling polyphonic parts, while using CV Gate for that more direct, immediate analog control of specific parameters, or for synchronizing older analog gear with newer digital equipment. It offers really enhanced sonic sculpting possibilities when you combine them.
Okay, this is great. So CV Gate isn't just some historical footnote collecting dust.
Right.
Let's really delve into the practical side for our listeners.
Mhm.
Where do we actually find CV Gate in modern music gear, and how can you put it to use in your setup today?
Oh, you'd probably be surprised by the sheer range of contemporary equipment that incorporates CV Gate now. It's really diverse. On the controller front, the Arturia Keystep series is probably the most obvious example.
Yeah, you see those everywhere.
Right, they're super popular. These controllers have dedicated CV Gate outputs specifically for controlling pitch and timing on modular and semi-modular synths. So you can use their keyboard, their arpeggiator, their sequencer directly with your analog gear. They even include a mod CV output, which is cool. You can assign that to control other parameters using the touch strip, giving you some versatile modulation options. Plus, they have sync in and out jacks that use gate signals for tempo synchronization between devices, which is a really practical tip for keeping everything locked in time.
They really do seem like a super accessible way to bridge different types of gear, old and new.
Yeah.
What about dedicated sequencers designed specifically for CV Gate?
Yeah, there are plenty of those too. The Korg SQ1 is another really popular and, importantly, affordable choice. It's a step sequencer, gives you two independent sets of CV Gate outputs.
That's nice.
Yeah, so you get hands-on control over melodic and rhythmic patterns for your analog synths and drum machines. It offers a very tactile way to program and perform sequences. Then you have things like the Electroharmonics 8-step program, which is cool because it puts a CV sequencer right into a guitar pedal format.
Oh, wow, and a pedal.
Yeah, perfect for controlling analog effects pedals that have CV inputs. Or the more experimental stuff, like the Make Noise 00, which is this touch plate-based keyboard and sequencer offering really unique gestural control over CV and gate.
Very performative.
Very. And for more complex, maybe generative or algorithmic sequencing, there's the Torso T1, which also outputs CV and gate, allowing for really intricate and evolving patterns. The landscape of CV Gate controllers is incredibly diverse now, catering to all sorts of different workflows and creative approaches.
Okay, and what kinds of devices can actually be controlled with these CV signals in a modern context? It's definitely not just limited to vintage synthesizers anymore, right?
Absolutely not. No way. We're seeing CV inputs pop up on a vast array of modern equipment. Semi-modular synthesizers are a big one, things like the Bastel Instruments Soft Pop 2 and Castle Drum, or the Make Noise Striga. They're specifically designed to be patched and manipulated with CV, really encouraging experimentation and sonic exploration.
Right, they expect you to patch them.
They do. And loads of effects pedals now include CV inputs for controlling parameters like delay time, filter cutoff, modulation rate, adding this whole other dynamic dimension to sound processing. And if you want to integrate your analog gear with your computer, your DAW, or other MIDI hardware, there are CV to MIDI converters that translate those analog voltage signals into digital MIDI messages and vice versa too, providing pretty seamless integration into modern production setups.
So the possibilities for crafting unique sonic textures and performance setups, they seem incredibly broad, almost limitless.
They truly are. And one of the most exciting aspects of CV Gate, for me anyway, is that the signals themselves don't have a fixed musical definition, you know? A CV signal that's controlling pitch on one device could just as easily be used to manipulate filter cutoff or panning, or even trigger an envelope on a different device that has CV inputs.
Ah, okay.
This really opens up avenues for unconventional sound design and those wonderful happy accidents.
You mentioned earlier using a key step to control the sound type on a Bastel Castle drum. That sounds like a perfect, practical example of that flexibility you're talking about.
Exactly. It's all about creatively rerouting the intended function of a control signal to achieve unexpected and hopefully interesting sonic outcomes. For instance, you could use the pitch CV output of a sequencer, not for pitch, but to control the decay time of a drum machine's envelope.
Oh, boy.
Creating these dynamically changing rhythms, that's where a lot of the real fun and sonic discovery lies with CV Gate, I think, just patching things up differently.
Okay, so for someone making music today, maybe they're mostly using MIDI or just software, why should they seriously consider incorporating CV Gate into their workflow? What are the tangible benefits it offers alongside or maybe even instead of MIDI?
Well, there are several key advantages, I'd say. One is just the directness, the immediacy. You physically plug in a patch cable and you instantly hear the result. There's no need to navigate complex MIDI CC assignments or software mappings in a menu somewhere.
Right, no menu diving.
Exactly. It's a very immediate, very tactile way to interact with your instruments, and I think that fosters a more intuitive connection.
That immediacy sounds really valuable, especially when you're kind of in a creative flow state and you just want instant feedback from your sonic manipulations.
Definitely. Another significant advantage is the sort of universality across different gear. Because so many different manufacturers and types of devices now include CV Gate, it makes it surprisingly straightforward to create unique performance setups by combining equipment from different eras, different origins. You might, for example, use a modern Eurorack sequencer to control a vintage analog synth and a contemporary CV-equipped effects pedal all at the same time.
And you touched on resolution earlier.
Yeah.
How does the control detail, the smoothness of CV Gate, compare to MIDI?
Yeah, this is a crucial point, especially for detailed sound design. MIDI control messages, your standard CCs, typically have a resolution of 128 discrete steps. Okay, you can get higher with NRPNs, but standard CC is 0, 1, 2, 7.
Right, 128 steps.
Control voltage, however, because it's an analog signal, it's continuously variable. It has theoretically infinite resolution. This allows for much smoother and more nuanced control over analog parameters.
Yeah.
You avoid that stepped zipper effect that can sometimes be audible with MIDI, particularly during slow filter sweeps or smooth pitch bends.
Ah, okay. So for achieving really smooth, organic, detailed control, especially in things like pitch or filter movements, CV can offer a distinct advantage in the actual sonic quality.
Absolutely. It can sound more fluid. And then there's the aspect of interconnectivity we talked about. CV Gate enables a very seamless integration of diverse analog gear, regardless of when it was made. And, as we discussed, that ability to creatively remap control signals, it just opens up this vast landscape of unconventional sound design possibilities. You can patch a CV signal to control parameters that maybe weren't originally intended to be controlled in that specific way, leading to really unexpected and unique sonic textures. For example, using an LFO output, maybe audio rate LFO, to modulate the sample rate input on a digital effect pedal can create some really bizarre and interesting artifacts.
That idea of creative remapping and the potential for unexpected sonic discoveries is definitely compelling. It really sounds like it encourages a more experimental, more hands-on approach to music creation.
It absolutely does. It invites tinkering. However, if you are considering venturing into the world of CV Gate, There are a few important practical considerations to keep in mind just to ensure a smooth experience.
Okay, worth knowing. What are some of the potential pitfalls or things you really need to pay attention to when you start plugging these cables in?
Compatibility is probably the key factor. As we discussed earlier, voltage ranges for trigger and gate signals can differ between manufacturers. You might encounter situations where you definitely need a converter box or module to go between, say, a v-trig output and an s-trig input. Similarly, you absolutely need to be aware of the CV implementation for pitch. Is it volts per octave or hertz per volt? If you're aiming for accurate, in-tune pitch control between different brands, always consult the manuals for your gear.
Good advice. Read the manual.
Yeah.
So it's not always quite as simple as just plugging any cable in anywhere and expecting it to work perfectly first time.
Mm.
A bit of research into your gear's specific specs might be necessary.
Exactly. It pays to know your gear. And finally, a very basic but crucial point, just make sure you have the correct cables. CV gate connections are most commonly made with 3.5mm mono jack cables, those little mini jacks you see on your rack.
The little ones.
But it's always wise to double check the specific requirements of your equipment because sometimes you might see quarter-inch jacks or other connectors, especially on older gear. Just avoid simple connection issues.
It's some really valuable and practical advice there. Okay, so to kind of bring it all together now, what are the essential takeaways about CV Gate that you really want our listeners to remember from this deep dive?
I think the key thing to remember is that CV Gate isn't just old tech. It's a fundamental analog control method, yes, with a rich history, but it continues to be a potent and incredibly versatile tool for modern musicians. It provides a really direct, immediate, and high-resolution way of controlling a huge spectrum of electronic instruments, offering unique sonic possibilities that often go beyond the realm of digital control.
And for you, the listener, getting your head around CV Gate, understanding it, it unlocks this wealth of new avenues for creative sound design, for unique instrument combinations, and maybe fosters a more intimate, hands-on connection with your actual music-making process.
Absolutely. Couldn't say it better. So having taken this deep dive into CV Gate, maybe here's a practical thought to consider, something to try. What unconventional connections could you experiment with in your own setup? What weird patching could you try just to generate sounds you haven't encountered before? What parameter on one of your instruments would you be intrigued to control with a voltage signal coming from somewhere unexpected? My advice, grab some patch cables, don't be afraid to experiment, mess around fearlessly, and just discover the sonic adventures that are probably waiting for you right there.
That's fantastic inspiration to just get patching. It's really exciting to think about the enduring relevance of these foundational concepts like CV Gate in the constantly evolving world of electronic music. Thanks so much for taking this deep dive with us today.
My pleasure. It's a fascinating topic.